Welcome everybody. So the last few days we've been looking at determining from percent composition how to write the empirical formula, and based off of the empirical formula, how do you write a molecular formula? Well, we're going to just real quickly review that information because it's valuable information. I know that we have spring break coming up, or we might be currently on spring break. And some of this information can be forgotten. So what I would like to do is just kind of review that. If you want to pause the video at this point and do this front section, the left side of the notes page, this is all a review. I encourage you to pause the video, work through the information that you can. If not, just watch the video and follow along. Okay, so the first thing we're going to do, first of all, I want to identify our ratios. We cannot forget our conversion factors. Here, that 1 mole is equal to 6.02 times 10 to the 23rd ions, atoms, molecules, or formula units. Any of those terms is equal to 1 mole. The next conversion factor is that 1 mole is equal to the molar mass of that substance in grams, and we find those values on the periodic table. So let's review here. It says find the number of atoms in 12.5 grams of helium. So what I'm given is the number of grams of helium, and I want to convert grams of helium to atoms of helium. So like we've practiced, I'm going to start with what's given in my T-chart, which is 12.5 grams of helium. And I convert 12.5 grams of helium to moles of helium first. And in 1 mole of helium, this is my molar mass equation, not equation, but my molar mass conversion. I'm using the periodic table to determine that. So when I find helium on the periodic table, I realize it's got a mass of 4.003 grams. So 1 mole of helium is equal to 4.003 grams of helium. But I want to go to atoms of helium, so I need to take this another step further. So I bring down my units. 1 mole of helium is equivalent to 6.02 times 10 to the 23rd atoms of helium. Now, you might be asking, how do you know this is 2 steps? Well, think of it this way. I'm given grams, and I want to convert to atoms. When I look at my factors, I'm given grams. Here are grams. Grams only convert to moles. I want to convert to atoms, which is this second conversion factor. So I've got to go from one conversion factor to the next conversion factor, so that requires 2 steps. Here's step 1, convert grams to moles. Grams only converts to moles in this case. And atoms convert, or moles converts to atoms here. So that's my second step. So now I do the math. 12.5 times 6.02. Oops, excuse me. 6.02 E23, all divided by 4.003. And that gives me a value of 1.88 E24 atoms of helium. Okay, so continuing our review between empirical and molecular formulas, which formula is the actual formula? So the molecular formula is the formula that tells me the actual number of atoms in a compound. And the lowest ratio formula, or the simplified version of that, is the empirical formula. It's the reduced version of the molecular formula. So which compound has the same empirical formula as glucose? So when I look at glucose, glucose has C6H12O6. So these are not in their lowest form. This is the molecular compound. So all 3 of these need to be divided by 6. So greatest common factor between those is 6. So when I do that, C6 divided by 6 is C1. H12 divided by 6 is H2. and O6 divided by 6 is O1, or just simply CH2O. So now I need to figure out which of the formulas given to me, A and B, has the same empirical formula. Remember, more than one different element or compound can have the same empirical formula because they might have the same ratio, but they'll never have the same molecular formula. So for butanone, I've got C4H8O1. Okay, well, the greatest common factor here between all of them is 1, unfortunately. So this one has an empirical formula of C4H8O1. Okay, it's the same thing. It's got the same molecular formula as it does the empirical formula. Which process of elimination tells me it's B, but why is it B? Well, C2H4O2, the greatest common factor between all those is 2. So when I divide C2 by 2, I get C1. H4 divided by 2, I get H2. And O2 divided by 2, I get O1. Pardon the bell, which is CH2O. And this happens to be the same. All right, so some more review here is determining the empirical formula and molecular formula of a compound that's 30.45% nitrogen, 69.55% oxygen, and it tells me the molecular formula mass is 92.0 grams per mole. So this is the molecular formula mass. Okay, so we're going to start with nitrogen. Nitrogen had a percentage of 30.45, which is 30.45 grams. And then I'm going to convert to moles. So 1 mole of nitrogen is equal to, on the periodic table, 14.007 grams of nitrogen. And when I convert nitrogen's grams to moles, I get 2.174 moles of nitrogen. So now I'm going to do the same thing for oxygen. So oxygen had 69.55%, which is 69.55 grams. And when I convert to moles, 1 mole of oxygen is equal to the molar mass, which is on the periodic table, 15.999 grams of oxygen. So when I divide my grams by grams, I get 4.347 moles of oxygen. Okay, so my next step is to divide by the lowest mole value. Well, my lowest mole value, let's see, I got 2.174 and 4.347. This is my lowest value. So I'm going to divide both of those by 2.174 and 2.174. So obviously, any number divided by itself is 1, and 4.347 divided by 2.174 is approximately 2, and these are my subscripts. So let's start filling in some information here. The moles of nitrogen we just determined, we already calculated that. It was 2.174, and the moles of oxygen, we already found that. It was 4.347. So my empirical formula, if these are my subscripts here, then my empirical formula would be N1O2 or just NO2. Okay, so now I want to find the empirical formula mass. So I'm given the molecular formula mass. I want to figure out the empirical formula mass based off of the empirical formula. So this is rather easy. The empirical formula mass is equal to, and let's see, I've got nitrogen in 1. So the mass of 1 nitrogen, 14.007 times 1, plus O2, so the mass of oxygen, 15.999 times 2 oxygens, If you type that into your calculator, if you're going to do it all in one step, use parentheses. But you should get approximately 46. Okay, now, so I'll go ahead and write that in the data table. Okay, formula mass. Now I want to find the molecular formula. So to find the molecular formula, you take the molecular formula mass and divide it by the empirical formula mass, which is the molecular formula mass was given to me up here, which is 92. So 92 divided by 46, my empirical formula mass gives me 2. This is my multiplier. So now what I do is I take that 2 and I multiply it by my empirical formula, which is N1O2. So 2 times 1 is 2. 2 times 2 is 4. So I get N2O4 as my molecular formula. All right, so all of that should be a review. Remember, we cannot forget this. Unfortunately, this unit is divided up by spring break. So you might forget some of these things. Hopefully your memory is refreshed by going over this. So let's skip on to the right side of this notes page, and this is where we're going to learn some new stuff regarding stoichiometry. So stoichiometry might sound like a foreign word, but stoichiometry is really just about ratios, and we've been discussing ratios this entire time. We know conversions, we know how to set up T-charts, so stoichiometry shouldn't be any different. So a mole ratio is one of the things that we're going to have to learn here. And a mole ratio compares exactly what it sounds like, the ratio of moles of my reactants and products from a balanced reaction, a balanced equation. The key here is that it has to be balanced. So yes, we are going to have to kind of remove the cobwebs of that section of our brains. We have to remember how to balance equations, and I'll show you the box method again in case you forgot. So here I've got a balanced reaction. All right, my balanced reaction is 2H2 plus O2 produces 2H2O. I know it's balanced not only because it tells me here, but I've got 4 hydrogens here, 4 hydrogens here, 2 oxygens here, and 2 oxygens here, so it is balanced, okay? So step 1, make sure the equation is always balanced. So now I want to figure out the mole ratios of hydrogen gas to water and oxygen gas to water. So you're going to have to be able to figure out and determine what the reactants and the products are in the equation, because they won't always be given to you. So H2, we know hydrogen is a diatomic element. This is a gas. O2, oxygen, is also a diatomic element. That's a gas. And H2O is water. Okay, so as if you didn't already know, this is water. Okay, so the question says hydrogen gas to water, so I want to know the mole ratio. So you just look at the coefficients. So find hydrogen gas, find H2O. So hydrogen gas, here it is, it's got a coefficient of 2. And water has a coefficient of 2. So this is 2 to 2, and I can always reduce ratios, and in this case it's going to be 1 to 1. So that was telling me for every 1 mole or 1 molecule of hydrogen, I've got 1 molecule or 1 mole of water. Again with the bell, sorry about that. I'm trying to record this before school starts. All right, my next one is oxygen gas to water. So oxygen gas is O2. Water, we should know, it's H2O. So find the coefficient for oxygen. There's nothing there, so it's implied that it's a 1. And water, we said, is a coefficient of 2. So I can't reduce that any further, so it's 1 to 2. My mole ratio of oxygen gas to water is 1 to 2. For every 1 molecule of water, 1 molecule of oxygen, I've got 2 molecules of water. That's all that says. So stoichiometry, we're going to use those mole ratios from a balanced equation, like I mentioned before. That's very important. And we're going to end up calculating the amounts of reactants or products. So give me a second to write this. We're going to determine the amounts of reactants or products. Okay. So we're going to determine the amount of reactants or products that are used or produced in a chemical reaction. Okay, so let's get to it. Like I said, we always have to have a balanced equation. Always have to have a balanced equation. If the equation is not balanced, then you will forever get the wrong answers. So let's look at it. There's your arrow, draw a line. H2 is 2 H's, put them in a box. N2 is 2 N's, put them in a box. NH3 is 1 N and 3 H's, put them all in a box. Now you count. 2 hydrogens, 3 hydrogens. Right off the bat, I know this is unbalanced, so I need to add hydrogens to the lower side. Now, when I do that, it only gives me 4, and I've got 3 on this side, so I'm going to add to the lower side. So I cannot just add 1 to say there's 4. I've got to add everything that is in this molecule. Okay? So now I've got 1, 2, 3, 4, 5, 6 hydrogens on the right. 1, 2, 3, 4 hydrogens on the left. So I'm not balanced yet. I've got to add another pair. So that gives me 6 on the left, 6 on the right, 2 nitrogens on the left, 2 nitrogens on the right. We are balanced. So now we count the boxes. So for hydrogen gas, it's 1, 2, 3. So my coefficient's 3. For nitrogen gas, it's 1. And for NH3 ammonia, it is 2. All right, so now I want to write the coefficients for that reaction. From left to right, it's 3, 1, 2. Easy. What do the coefficients represent? Coefficients represent the number of molecules and or the number of moles. Okay, so when I read this equation, I could say 3 molecules of hydrogen plus 1 molecule of nitrogen produce 2 molecules of ammonia. I can also say 3 moles of hydrogen plus 1 mole of nitrogen produce 2 moles of ammonia, NH3. So the coefficients represent either molecules and or moles. Okay, just know that both of them are represented by the coefficients. Okay, so look at our mole ratios. So I want to write the mole ratios from nitrogen to ammonia. So you have to be able to identify which is which. So nitrogen in my equation is N2. Ammonia is NH3. So how many nitrogens do you have for every ammonia? So nitrogen has a coefficient of 1. Ammonia, NH3, has a coefficient of 2. So my ratio is 1 to 2. Okay, moving on. Hydrogen, which is H2 to nitrogen, N2. Hydrogen has a coefficient of 3. Nitrogen has a coefficient of 1. I cannot reduce that, so my ratio is 3 to 1. Easy stuff. All right, so now how do we convert from moles of one substance to moles of something different? So number 4 says use the balanced reaction above. Determine how many moles of hydrogen gas must react to produce 12.25 moles of ammonia in H3. So we're going to use the reaction that was given to me up here. What we said was 3 moles of hydrogen gas plus 1 mole of nitrogen gas produces 2 moles of ammonia. Okay, so we can't forget those ratios. All right, so first things first, we're going to continue moving on like we've practiced. Identify what is given to you. So I'm given 12.25 moles of ammonia. So I'm going to start up my T-chart as 12.25 moles of ammonia in H3. Okay, so I'm going to set up my T-chart like so. Okay, now we've practiced converting or bringing down the unit. So my unit's moles of ammonia. So I'm going to continue to do that. So I'm going to rewrite moles of ammonia. Now, I want to go from moles of ammonia to moles of hydrogen gas. So this was given to me. This is unknown. Okay? So for this, I'm going to write what I want to convert to. Moles of hydrogen gas, H2. Now, the only time that I can go from moles of one substance to a different substance is if I convert from moles to moles. Okay? Any other time, if I'm converting from moles to atoms, I must go from moles of ammonia to atoms of the same thing. Okay, or moles to grams, it's got to be moles of the one substance to grams of the same substance. The only time I can go from moles of one substance to a different substance is if I go from moles to moles. This right here is my mole ratio. Okay, and this is where we look in the equation to determine it. This is my mole ratio. So when I look up in my equation, find the coefficients for hydrogen gas and ammonia. So hydrogen gas, where am I at? Here we are. Hydrogen gas had a coefficient of 3. Ammonia had a coefficient of 2, so my ratio is 3 to 2. So that is what I transfer down here. 3 moles of hydrogen gas, 2 moles of ammonia, and now I calculate just like I've practiced before. So 12.25, everything on the top gets multiplied, and the top is divided by the bottom. So 12.25 times 3 divided by 2 gives me 18.375 moles of hydrogen gas. There's my answer. Okay, so because this is a mole conversion, this is a mole ratio, I'm going from moles to moles. I know that we've practiced whatever number you put down here, moles is always 1. There's always 1 mole. Well, that's not true for this type of conversion. Okay, if we were going from moles to particles, then I would have 1 mole. If I was going from moles to grams, then I would have 1 mole. But because I'm going from moles of one substance to moles of a second different substance, okay, it could coincidentally be 1, but you have to look at the the coefficients in the equation to tell you. So let's try another one. So it says, how many moles of hydrogen gas will react with 9.75 moles of nitrogen gas? So remember, nitrogen gas is N2. So this is given to me. And I want to go from moles of nitrogen gas to moles of hydrogen gas, which is H2. Okay, so I'm going to set up my T-chart. Okay, I'm going to write what's given to me, which was 9.75 moles of nitrogen gas, which is N2. So I bring down the unit just like I've been before, moles of N2. And now I want to convert to moles of something different, which is hydrogen gas. So I can make that conversion from one substance to something different because this is my mole ratio. So now you'll determine what the coefficients are for hydrogen and nitrogen. So when I look up at the equation, the coefficient for H2 was 3, and the coefficient for N2 was 1. So my mole ratio from hydrogen to nitrogen is 3 to 1, based off of my equation. 3 to 1. Okay, so now let's calculate. 9.75 times 3 divided by 1 gives me 29.25 moles of hydrogen gas, H2. There you go. That's the extent of a mole-to-mole conversion. Okay, let's try another one on the back. So now you're given the equation, and I would like you to try this one on your own as practice. You can go ahead and pause the video. If you're not sure or you'd just like to check your answers, you can play the video, start the video up again, and I'll share that with you. Start by balancing the equations, determine your coefficients, and then convert from moles to moles. All right. So I've got C plus H2 produces CH4. So let's balance this equation. I've got 1 carbon, 2 hydrogens, all in a box, 1 carbon, and 1, 2, 3, 4 hydrogens, all in a box. So now I count 1 carbon, 2 hydrogens, 4 hydrogens. So this one's easy because all I need to do is put 2 hydrogens over here, and I've got 4. So my coefficients are 1, 2, 1. 1, 2, 1. So what are the mole ratios from hydrogen to carbon? So here's hydrogen, here's carbon. The ratio is 2 to 1. Okay, let's try hydrogen to methane. So methane, you might not be able to tell, but I know this is carbon, so this is not methane. I know this is hydrogen, this is not methane. So by process of elimination, this molecule has to be methane. Methane is carbon tetrahydride, which is CH4. And we already know that hydrogen is diatomic H2. So when I look up at my equation, the coefficient for hydrogen is 2, the coefficient for methane is 1, so my ratio is 2 to 1. So let's practice our mole-to-mole conversions. How many moles of carbon are needed to react completely with 15.5 moles of hydrogen? So I'm given 15.5 moles of hydrogen, and I want to know how many moles of carbon that is. So I'm going to start with my T-chart. And I'm going to write what's given to me, which is 15.5 moles of hydrogen. And then I'm going to bring down the unit, moles of hydrogen. Now I want to go from moles of hydrogen to moles of carbon. So again, the only time I can go from one substance to something completely different is if I go from moles to moles, because this is a ratio. So looking back up at my ratio up above, from hydrogen to carbon, we said from hydrogen to carbon, our ratio was 2 to 1. So 2 moles of hydrogen for every 1 mole of carbon. So 2 to 1. Now I calculate. 15.5 times 1 divided by 2 gives me 7.75. Moles of carbon. And the last one, how many moles of hydrogen H2 react with carbon to produce 5.5 moles of methane? So I'm given 5.5 moles of methane. Remember, methane is carbon tetrahydride, CH4, and I want to know how many moles of hydrogen that is. So I'm going to set up a T-chart. and I'm given 5.5 moles of methane, CH4. So I bring down the unit, moles of CH4, and I want to convert from moles of methane to moles of hydrogen. And I can go from one substance to another because I know the mole ratio. We already figured that out up above. The ratio of hydrogen to methane was 2 to 1. So for every 2 hydrogens, there are 1 molecule of methane. So 2 and 1. Now I calculate. 5.5 times 2 divided by 1 gives me 11 moles of hydrogen gas.